Hello everyone, I'm Sotaro Katayama from Kyoto University, Japan. Today I'd like to talk about quasi-static contact-rich manipulation by linear complementarity quadratic programming. This work was done at Omron Scientific X Corporation as an internship, and this is a joint work with Tatsunori Tani-ai and Kazutoshi Tanaka, who are with Omron Scientific X Corporation. First, I'd like to introduce our motivation of contact-rich manipulation. This figure shows a motivative example. Let's say the gripper wants to manipulate this box without grasping it. Because the gripper cannot grasp the object, to achieve this goal, the gripper has to leverage the contacts of the box with the ground and wall. A unique feature of this manipulation is that the contact mirrors, that is, on-off and stick slide of the contacts, change throughout the manipulation. The challenges of this problem come from that planning and control of this kind of manipulation need decision-making on discrete contact mirrors as well as the continuous control actions. This is particularly difficult when the online planning is required. For this problem, we propose an online planning method based on the linear complementarity quadratic programming called LCQP. In our LCQP framework, we describe the contact mirrors implicitly using the complementarity constraint. For example, the distance between two objects, described as function phi, and the normal contact force between these objects, described as lambda, form a complementarity condition. By solving an optimization problem subject to such kinds of complementarity constraints, we can realize simultaneous decision-making on the contact mirrors and continuous control actions. However, this optimization is hard to solve in general. Our contribution is a set of formulations that realizes the first and robust optimization. This is a brief diagram of our problem settings. We consider an online local planner that determines the end effector force and contact forces based on the current state of the robot and object. We utilize LCQP to take the contact complementarity into account in the planner. Next, we introduce the quasi-static model of the manipulation planning. Let Q be the configuration of the actuated object, that is, the end effector of the manipulator, and QU be the configuration of the unactuated object, that is, the box. We then consider the quasi-static time evolution of the total configuration Q, composed of QA and QU, as a dynamical system of this manipulation problem. To take physical constraint into account, we consider force and moment balance around the unactuated object. To describe the physical constraint of contacts, we utilize complementarity constraints. The first complementarity constraint is imposed between the normal contact force and contact distance, which means that either of which should be always zero. Further, the complementarity constraints regarding the Coulomb frictions are enforced, which represents the stick and slide of the contacts. Hereafter, we call the set of these complementarity constraints as the contact complementarity constraints. Now, we formulate the LCQP problem. The goal of our local planning is to find the position and the contact force command as the next time step t plus 1. That is, find the increments delta qt and delta lambda t. We describe the tasks as a function g. Then we introduce an objective function to achieve this task, with regularizations on the velocity and contact forces. This objective function is non-convex in general and difficult to minimize, particularly under the complementarity constraints. Therefore, we approximate this objective function around the current position and contact forces, specifically using the Gauss-Newton method. We consider this optimization problem subject to the contact complementarity constraints. To obtain the structural optimization problem, we also linearize the contact complementarity constraints. Further, we introduce a slack variable to relax the constraint, that is, to make Z hard constraint into soft constraint. This can improve numerical robustness, that is, this prevents failures in finding feasible solutions under disturbances, such as sensor noises and model mismatches. Finally, we summarize the LCQP problem. We seek that Q and that F that minimizes the approximated cost function subject to linearized and relaxed constraints. Next, we demonstrate the effectiveness of the proposed method through physical simulations. The first task was to pivot and stand up a box without grasping it. Our method automatically determined the contact moves and control actions in real time and succeeded in the task. Our method could achieve other contact-rich tasks as shown here. In these tasks, our method could leverage the various contacts and find the desired position commands. Finally, we introduced limitations and possible extensions. Limitations of the proposed method are dynamic tasks, which involve non-negligible velocity and accelerations. For example, it is difficult to stabilize static force balance in flipping of a half cylinder. A possible extension is to incorporate dynamical model into the LCQP formulations. I would like to conclude our presentation. Our motivation is to realize online execution of contact-rich manipulation that involves decision-making on discrete contact moves and continuous control actions. For this problem, we propose an online local planning method using the LCQP. Our formulations realize fast and robust online optimization with a contact complementarity constraint. We demonstrated its effectiveness through various contact-rich manipulation tasks. That's all of our presentation. Thank you for your attention.